Okay, so today's problem is find minimum in rotated sorted array. Let me actually pull back to the blind 75 list real quick here because this is actually the start of a new topic. We just finished up the singular stack problem that is on the blind 75, and we are moving on to the binary search section. So unfortunately, there is not like a sort of default binary search problem. They start with like a twisted problem. So we're going to talk about the binary search algorithm in general and why we like it, and then we'll apply it to this problem. Let me think about, yeah, actually, unusually today, we actually won't start with the problem itself. Let's talk just very briefly about binary search. If you've never heard of it, we call it binary search. Well, the search part of that is that we are looking for usually a particular element, although it could be something like yeah, I guess the standard version of binary search. We're looking for a particular element and we have sorted data. So those are like sort of the two conditions for using binary search. So maybe we have data that looks like this. So you got like 2, 5, 6, 7, maybe we'll say like 9, 12, and 13. I just want this to be big enough to do a couple iterations of the search. We won't do the whole thing. But here's the core of it is if we have sorted data, historically what we've said is if we want to find a particular element or figure out if an element is present in the array, we have to do something like walking through each element, and if the thing we're looking for just so happens to be the biggest thing, then we end up having to look through each element once in order to find the element we're looking for. So if we're looking for 13, hypothetically, we go all the way from the front to the back until we find the element or that we confirm that it's there. Okay, so we would like to be better than linear time, better than O of n. How can we do that? Well, the idea behind binary search is that we can split the array in two, and we'll do this by just tracking indexes here. So for example, I'll have like left and right here that start at the beginning and the end of the array, and we can use those indexes to track or to calculate what the middle would be. So in this case, the indexes are 0 and 1, 2, 3, 4, 5, 6. And just as a rough way to get what the middle is, we can say, hey, to calculate the middle, just go ahead and do the right plus the left and cut that in half. And we'll go ahead and like do integer division on that. So like if it's not nice and clean, it's not clean integer, we'll just lop off the remainder and always round down. Okay, so this is going to put the middle pointer at array index 3. And because we're dealing with sorted data here, when we want to look for a particular element, so let's say we're looking for 12 is our target. What we can do, since we know that it's sorted, is we can compare the target to the middle and chop off basically half of the array at any given time. Okay, so for example, in this situation, if we're looking for 12 and the middle value is 7, well, since this is a sorted array, we can confirm that we never need to look in the left half. We can just look in the right half, right? And so the way that we will reflect that, instead of, we don't want to actually manually get rid of all the data, what we'll do is we'll say, okay, I'm going to recalculate middle in just a second, but for now, I'll go ahead and move this left pointer over to where middle was before. Okay, so now this guy is going to be at index 3. And again, we know that we can do this because the array is sorted, and if we're looking for something that was bigger than this element, it's got to be in the right half, right? Okay, so similar vibe to before, we'll say, okay, we've got left pointing at 3, right pointing at 6 for the indexes, and we're looking for 12. Let's calculate the middle. So we'll do like 3 plus 6 divided by 2, and this is 4.5, which will round down to 4. And this tells us to put the middle index at 4. And once again, we say, okay, the target is 12. It's bigger than 9, so we're definitely not looking in this section. We're looking to the right half. And again, what we are going to do to signify that is we're going to take the left pointer and move it over to where the middle was before. Okay, so this is now 4. And finally, on this last run, what ends up happening is that the target 12, well, first of all, we have the middle of 4 and 6. I won't do this calculation by hand, but it's 5, so the middle point's here. There's a couple ways to handle it from there. Since we're, in this case, the way I've kind of set this up is we're searching for a target value, we can just check if the target value is the same as what the middle index is pointing at and then just end early. Alternatively, we can like keep this going until like left and right are pointing at the same place. So there's lots of different ways to set up kind of the binary search part of this. In this case, we can stop because the middle pointer is pointing at the thing that we're looking for, and so we can confirm that it's there, and we can even confirm its index if we want to. So that's how binary search works in general. And again, the big strength of this is if we're working with a really large data set, cutting off half of it at a time is a really huge deal, right? And so generally we say that the time complexity for binary search is log n, specifically log base 2 of n, because we keep chopping it in half is the idea. So if you needed to know how many times it would run, it's like how many times can you chop it in half before you get to a singular element, which is going to be log base 2 of n. Okay, so let me think about this real quick. Yeah, so just to run through this, because I think we're going to use a different version of it. If we didn't want to do the whole like check if the middle is the value thing, another way that we could handle this is by just continuing this pattern. So for example, if we were not being smart about checking the middle, we could say, hey, 12 is actually still bigger than 9. So the algorithm will tell us to move this guy over. Which puts us at 5 and 6, and then this is going to make the middle point here, because 5 plus 6 is 11. 11 truncation division 2 is going to be 5. And then since this time the target is not bigger than what left is pointing, or sorry, not bigger than what the middle is pointing at, this is going to cause us to move the blue pointer in, and as you can see, everything is pointing at the same thing now. So another way we can kind of detect the end condition of binary search is by saying, hey, left and right are at the same place. This means we must have settled on an element. Okay. Now the assumption that I'm also kind of running with here is that the element is actually there. If we just never find it, that's like kind of another scenario we would have to deal with. So for example, if there was no 12, we would have to do some extra checking for like, we've hit a situation where we should have found it, but it wasn't there. We don't have to deal with that in today's problem, so we won't cover it because we got to get to the actual problem. We haven't read it yet. But this is how binary search works in general, and today's problem is a little twist on that. So if you were confused about binary search, that's a little overview on it. Yeah, so let's look at the actual problem now that we got that under our belt, and we'll talk about how it relates. So today's problem is find minimum in rotated sorted array. And here it is. You are given an array of length n, which was originally sorted in ascending order, like what we saw earlier, but it has now been rotated between 1 and n times. It actually doesn't matter how many times it's been rotated, because if we rotate it over n times, it'll just get back to the original rotations, so it doesn't super matter, but it's been rotated. So for example, if we have the array which is nums 1 through 6, that might become, if we rotate it 4 times, so this is rotating everything to the left once, basically. To the right once. It might become 3, 4, 5, 6, 1, 2. So everything shifts over, and if it hits the end, it just rotates to the front. Okay? And then if you rotate it n times, so 6 times, it just goes back to where it was before. So if you rotated it 7 times, then it would just be the original plus 1 rotation, right? Okay. So they point out a couple things here. Notice that the rotating the array 4 times moves the last 4 elements of the array to the beginning. Rotating the array 6 times moves the last 6 elements to the beginning. So it returns it to its original positions. Okay, and then assuming that all elements in the rotated sorted array nums are unique, so we don't have any duplicates, nothing that will be equal, we want to return the minimum element of the array. And then they clarify one kind of important thing for this problem, which is that a solution that runs an O of n times, so just look through all the elements and get the smallest one, is trivial. It's quite easy to do. But they want us to write an algorithm that runs an O of log n time. And so the relation here to binary search is we want to do the same behavior of being able to sort of disqualify half of the array at a time and look in the other half. Okay. We won't go through the examples in great detail here because they're very obvious. It's just pick the smallest one. The method is what we're interested in. But the constraints, the length of nums will be between 1 and 1,000. The elements of nums will be between negative 1,000 and positive 1,000. So pretty manageable stuff here. All right, so let's talk about it. We'll actually do, we'll use their array example here, the beginning one. So here is what the array might look like when it is not rotated. And in fact, we'll just write out the rotations here so we can see them, because we can do some analysis on like what has to happen. So if we rotate it once, the 2 is in the front, the 1 heads to the back. And as they noted in the explanation, the number of times that you rotate, they did the rotations in the other order. It doesn't matter. So my observation is actually not correct because I've rotated in a different order than they did. The point is, there's still some structure to these guys, right? So here's the different possible rotations we can get. And there are still sections of this that are sorted. Now again, when we think about eliminating half of the array, we got to make sure that we eliminate the correct half, right? That's like obviously important to this problem. So if we think about this generally in terms of the binary search algorithm, we would put a left pointer, a right pointer, and we'd be interested in what is in the middle of those two, right? So this is index 0 and index 5. And this means that the quote-unquote middle would be over here at 2. Okay, I'm also, just for the sake of demonstration, going to go ahead and circle where the minimum is in all of these guys. Okay, so here's the general idea behind what we need to do. We've got the middle over here, right? In all of these guys, the first step is to kind of look right there. And there's going to be some... What the hell is that? I didn't draw that. Did I? That's so sad. GoodNotes said that was not a rectangle. Try one more time. Okay, I don't know what that is. Can I not draw rectangles anymore? This is so sad. Hello? Is it just not good enough of a rectangle? Oh, it was just a bad rectangle. That's so sad. Okay, okay, so here's the different rotations of this array that we can get. I'm gonna see if I can okay, there we go. Oh, I don't need all that. I don't need all that. Okay, God. Okay, oh, what's going on? Why is it so ugly? This is so sad. Let me try this one more time. It really doesn't want to draw a rectangle. Okay, we're gonna have to go for it. So here's what we would say are the middle elements, right? And what I want to point out here is that the minimum, we can kind of analyze, we can sort of analyze the relationship of the middle to, well, in this case, we've already got the left and the right pointer. Those are the ones we're interested in, right? So here's some observations I want to make. When we compare the middle to the left, we want to look for a pattern that consistently gives us the same response as far as which half is the minimum in, right? So if we compare these to the left, in this guy and this guy, well, let me think. We'll go ahead and say that the middle is I think it's arbitrary, but let me just chew on this for a second. We'll go ahead and say that the middle is part of the left section. Not that it super matters. We'll talk about the algorithm in detail in a sec. But in short, you'll notice that this is inconsistent, right? If we compare these two elements, in the first example, the left element is small and the middle element is big, and the minimum is on the left. In the last comparison here, we have the left element is bigger than the middle element, but the minimum is still on the left. And so this is not a good comparison for us to make because it doesn't always produce the correct half of the list or the correct half of the array, right? It's ambiguous as to whether or not this is actually related to where the minimum is. And kind of the reason for that is because just because a section of the array is sorted does not mean that it actually contains the minimum, right? So for example, as we're looking through these, like for example, this one, this half, it is sorted, right? But just because we have a small element over here doesn't really guarantee that it's the overall smallest, or that, there's no good way for us to tell. So in short, comparing the middle to the left element is not a great idea because some section of this array is sorted anyways, right? And it's not helpful for us to know that because it doesn't tell us if this is the entire sorted section or if it starts from the minimum. Okay, so now let's do the comparison the other way. Let's say we're comparing these middle elements to what's on the right over here. Okay, so in the first example, if we compare 3 to 6, what this is going to tell us is that that entire right half is sorted, right? Well, if the entire right half is sorted, then this means that either the middle is the smallest element, or the left portion also has some sorted stuff and the minimum is in there, right? So that would be true for like this guy. I'm starting to see why they did the order in the other direction, or the rotating in the other direction. Anyways, my point here is that this guy, so 3 is less than 6, right? 1 is less than 4, 2 is less than 5. In all of these scenarios, what we're saying is, hey, this section is sorted. That means the middle is a candidate for the minimum, but there might be something even smaller to the left. And that's true for all of the ones that I've circled here, right? So we need this kind of, well, the proper term here is this invariant. This is always true, no matter how we do the algorithm. If the middle element is smaller than the right element, then either the middle element is the minimum or the minimum is even further to the left, right? So either this is like the start of the sorted section and that's our minimum, or this is the middle of the sorted section and the real minimum is somewhere over here to the left, right? Okay, so that's a good basis. And then what would be the scenario where, in fact, let me do this in different colors here. So some of these have the situation where left or middle is smaller than right. And I'm not writing this, but these are the actual values, not the indexes. So some of these have the scenario where middle is less than right. And in that case, the minimum is like at or to the left of the middle. Okay, but we also have obviously these other ones, which is the opposite situation. In these situations, the middle element is greater than what's on the right-hand side, which means, since this was originally sorted and now it's being rotated, what that means for us is that the section that we're looking at has the reset somewhere in the middle of that. Like somewhere in that section, it resets, right? So in this case, since the reset happens somewhere between these two elements, that means that this element is not itself the minimum, but everything over here could be the minimum, right? So we don't know where the reset is yet. We'll have to do a little bit more sleuthing to figure that out, but we've at least confirmed that it behaves this way overall. So assuming that the middle is greater than the right, then what do we want to do? Or what's our conclusion? This means that the minimum is to the right of middle. And basically now we just rinse and repeat. So like I talked about earlier with binary search, the mechanism that well, I guess I don't have it animated there, but the mechanism that we use for this is we shift either the left or the right pointer over in relation to the middle to kind of close up the window, to eliminate half of the array, right? So if mid is less than right, we can eliminate, maybe I should show this actually. If mid is less than right, then we can eliminate the right half. Oh, this is the wrong color. And the wrong, no, wait, that's right. We can eliminate the right half. And notice in none of these scenarios did I cross out the middle, right? And then if mid is greater than right, then we can eliminate the left half, including the middle itself. Okay, And if we repeat this process, the left and the right will close in on each other until eventually they actually hit each other. And again, that's the reason we're guaranteed that they're going to hit each other, is because we're told, well, obviously there will be a minimum, right? And we're also told that there's no duplicates, so there's no point where we'll stall and they'll just be equal to each other. Which, by the way, is why I don't have to include what happens if middle equals right, because we know that they're all distinct. Okay, so yeah, we'll repeat this process until left and right are at the same place, and that's going to be our guy. Yeah, I kind of wish I had gone through... Well, yeah, let's actually go through... I forgot I did the binary search explanation at the beginning, so we don't have a ton of time, but I think we have enough time to go through just like a full example of this. So if this is the specific array that we're working with, for example, we'll start left here, start right here, and this is again 0 and 1, 2, 3. I actually knew that that was 5. I don't know what you're talking about. I definitely knew that off the top of my head. And this means that the middle index, quote unquote, is going to be 2. Again, the way that this algorithm works overall, we'll say if the middle is less than the right, then we know that we can get rid of the right half. And if the middle is greater than the right, then we can get rid of the left half. Okay, so let's give it a shot here. We compare 5 to 2. 5 is bigger, so that means that we know that the minimum is on the right. There's a reset somewhere over there. We don't know where it is yet, but we'll go ahead and take these guy and move it over here. And we can actually pass over because, again, if it resets somewhere after here, then that means this element itself is not actually a candidate for the minimum, right? So we'll move the left over here. Okay, and now left is at index 3. Okay, we'll recalculate the middle. So what's the middle between 3 and 5? Hopefully you know that it's 4. Okay, and we ask the same question. How does the middle compare to the right? 4, well, it's not 4 factorial, 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 factorial. That's not correct, massive membrane. I apologize. That is way too big. Yeah, it's 4. Sorry, I get that joke made to me a lot, so now I have to curse you with the knowledge. Anyways, okay, so at this point, we again compare the middle element to the right element. How does 1 compare to 2? Well, 1 is less than 2. And again, what this tells us is that the minimum that we're looking for, since this chunk is sorted, that means it's either here or it's somewhere to the left of here, right? Well, we've already eliminated all this stuff, so that means it's somewhere in this section right here. Okay, so what are we actually going to do? Well, in practice, what we'll do is we'll move the right pointer over to where middle was. Again, since the middle was actually a candidate for minimum, we're going to put it right where it was before. Okay, so now we've got 3 and 4. We've got 6 and 7. Just kidding, we don't have 6, 7. Okay, and once again, we recalculate the middle. So what's the middle between 3 and 4? Well, it's a little bit weird, but if you did 3 plus 4, which is 7, divide it by 2, that's 3.5, which will round down. And so the middle goes here at 3. And so again, we ask our question, how does the middle relate to the right? Well, the middle in this case is greater than the right, which means that the minimum is to the... Hold on. Did I say that right? Yeah, the middle is greater than the right, which means the true minimum is... Okay, yeah, I was sorry. I totally brain farted there. I was like, aren't we looking for 6? I forgot we were looking for the minimum. So it's to the right of mid, which means we are going to move the left pointer to the right of middle, just 1 over from middle. Okay, so this guy, we don't need it anymore because we're going to move this guy over here. And this is finally the situation that we were waiting for, which is the left and the right are both pointing, or boink. The left and the right are boink. They're both pointing at the same place, and that means that we're done with the algorithm. That means that we have found our minimum. We're guaranteed that it's there. We're guaranteed that it's unique. So we know we're going to hit this situation eventually. And that's that. So let's code her up because it's actually quite short to code it. So we definitely need a left and a right pointer. Also, if anybody has any questions, throw them in the chat, or criticisms, or good things that happened to you today, or song lyrics that you've been thinking about. Okay, so we've got a left and a right pointer. I'm going to initialize them to 0 and the length of nums -1. And then we loop. Wow, there's really not much to this. Okay, so I'm going to say while left is less than right, which means when they hit each other, we're done, right? Okay, and then here's our situation. Again, I'm going to refer to the notes that we made over here. Here's our situation. If middle is less than right, so nums, oh, we need to calculate the middle. So every round of this, we're going to recalculate the middle. Actually, I think this is the easier part. For this particular one, the thinking is like, oh, you have to really get it right. And low-key, the last time I did this, I really fucked it up. Like, I like had just gotten things so mixed up in small ways. Anyways, once you have it down, the code is actually pretty reasonable. So the first thing we need to do for every one of these loops, we're going to recalculate the middle. And I'm just going to say it is left plus right, truncation division with 2. Okay, and let me slide this over. Okay, now based on the value there, so if nums middle is less than nums right. Okay, so this is the situation where we've got small number here, big number here, and this means that the section is sorted, but there might be more sorted stuff to the left. So that means the true minimum is somewhere over here, right? And this means we need to move that right pointer over to where middle is right now. Okay, and the alternative, so since it's only 2 conditions here, I'll say else. So if we hit this condition, that means that the middle is greater than the right. We have a situation like, well, the second one right here. So 4 compares to 1. Well, since there's a small number to the right, which is not usually what should happen for a sorted array, right? This means that there's a reset somewhere between here and here, where it goes down to the minimum and starts counting up again, right? And so what this means is that this guy itself is not a candidate because the reset happens after it. Instead, we're going to move that left pointer to whatever the middle was, +1. Okay, and again, eventually we're guaranteed that we're actually going to hit the minimum. And so at this point, we know that left is the same as right. And so we can either return nums left or nums right. I'm just going to do nums right because, I don't know, that feels better to me. Okay, and that's it. I'm like 99% sure this is correct, but you know me. I love to fuck something up at the end. Nope, we're good this time. Oh, thank God. Okay, I want to point something out actually because I sort of glossed over it in the explanation. There's actually no requirement, and I'm sure some of these test cases, they don't have to be like consecutive numbers here because they just need to be sorted, right? So this could have been like 10, 20, 30, 40, 50, 60, and it works the same way because we just care that that order is preserved. Heck, these could be letters if we wanted, and they would work the exact same way. Great. And that is that. That's like right on the dot. That was exactly 30 minutes. So that feels good. Questions, comments, concerns, criticisms, Bible verses that you like, song recommendations. Do any of the test cases use duplicate numbers? No, it was actually one of the problem constraints that the number, I can't remember how they phrased it. Let's take a look. All the elements in this rotated sorted array nums are unique, so no duplicates. If there were duplicates, I think we can still do this. We would probably need to make some tweaks to like some of the internal logic on like, well, yeah, then this is weird because what if the duplicate's the, yeah, you would basically you just have to add logic for like, what if it's equal to? Then does that mean that this is the minimum? Like you'd have to do some extra stuff to it. But with that said, if there were duplicate numbers, our first step would probably just be to deduplicate if we're being honest. That's probably the most straightforward way to handle that, right? I'm interested to know though, and maybe I'll do my own testing to see if we could still do it with the binary search format. My hunch is no, because then like you lose the sortedness, right? Like if you had a if your sorted unrotated array was like 1 2 3 4 5 6 6, and then you rotated it and it became 6 1 2 3 4 5 6, the logic is now weirded out, right? Because there's no like semblance now of like where is the like we can't use the sortedness in the same way anymore, if that makes sense. I think. I don't know. I might have to do my own digging into this, but that's my hunch. So don't take that as gospel, but that's my hunch. Okay, any more questions, comments, concerns, anything? Okay. Well, it's only 3 of you guys, but I'm going to encourage y'all to come to our mock interview night, Thursday night, so you can practice doing this yourself. Because you won't be interviewed by asking someone, they won't ask you to listen to someone explain a problem. You got to do it on your own, girl. It's crazy. It is this Thursday. The mock interview portion is from 4 to 6. And then we'll have a movie night after from 6 to 8. Damn. Midterm 5 is crazy. Understandable, though. Yes, it will be in person. Yeah, come for the movie. It will be in person. We are in the College of Business, room 139A. If you go to the announcements channel of this server, it will be, the info's in there. And if you want to RSVP, that'd be nice, just so we know how many people are coming. But you don't have to RSVP. We'll just see you there if you want to pull up. And then, Jahan, if you want to... Well, I know if you've got midterm prep, no pressure at all. But if you want to come for the first section of it, I'll interview you personally if you want, so you can get some practice and then you can head to your midterm. But you don't have to. I just wanted to say it's an option. Because it'll be like partner programming or partner interviewing. So like you'll interview someone and then they'll interview you. So if you drop by, I can, give practice. It'll be fun. Anyways, we'll call it there. But I mean, by all means, prepare for your midterm, But we would love to see it, and definitely stop by for the movie. I think we're going to watch It's the Great Pumpkin, Charlie Brown. But if the student life office asks you, I didn't say that. We're watching Hereditary because it's approved, which is crazy when you think about it. But I think it's the licensing thing. Anyways, sorry, I keep talking. Oh, I think we're gonna watch. It's the Great Pumpkin, Charlie Brown, because it's cute and like autumny. It's a fun movie. It's not. I mean, it's nothing. Well, I was gonna say it's nothing groundbreaking, but low key, that shit slaps. Great movie. Okay, we'll call it there, guys. Have a great night, and I will see you online. Maybe if you would like. I would like that tomorrow night.